All right, hey, well, welcome back. Let's get started yet again. Looks like I got a lot of stuff in my way. Let me just kind of straighten it out here a little bit so I can have some room to work with. But we are starting, what chapter is this? 10, believe it or not. And I'll begin by saying this is our last chapter on mechanics. And so we've done quite a bit with mechanics. And this chapter 10 is kind of the last piece before we go into other pieces of physics. And so usually about this time, students are like, okay, I've seen enough of mechanics. Let's move on to other things. And I'm kind of feeling that right now too. So one last chapter here on mechanics, and it's an interesting and a bit of a challenging chapter. My warning for you will be that we are going to look at rotations, and we've looked a little bit at rotations already. And now this is our second significant chapter on rotations. The good thing and bad thing about rotations is, and I'll start with the good thing, is that everything that we've already done for translational motion, we can then think about and apply for things that are rotating. And so you'll hear that theme for this next hour, and I'll keep saying, okay, remember what we did for translational motion? Let's think about it for rotational motion. So the good thing is a lot of this you hopefully will feel somewhat comfortable with. You'll go, oh yeah, that's kind of the same thing. It will be a bit of a challenge to kind of change your thinking from going, okay, the car moved across to the wheel rotated. But it's the same general idea. And so a big goal here is to get you to see how everything we did for translational motion, we're going to repeat here for translational motion. I mean, for rotational motion. So that's the main thrust. And the good news is that you won't feel like this is something new, something more piece to our mechanics. It's just an extension of our mechanics. Now, maybe the bad thing, though, is that means in this little chapter, we're going to try to do all the other chapters we did for translational motion. We're going to try to fit them into this one chapter real quick. And that's a lot to ask. And so we did kinematics, we did dynamics, we did principles like conservation of energy and conservation of momentum, and all of those we're going to try to fit in this 1 hour or 2 hours here real quick. So let's talk. All right, so I'll begin by maybe putting here on the board that where we are here is chapter 10. As I just said, we are going to then be studying rotational motion. And probably the best way to begin is to go back to a picture that you've already seen. And I've put it here from your author's book here, or your author's picture here. And he says, let's just take an object that spins. And so he's got this little disc. For me, I'll just kind of pick up this wheel right here and go, okay, I'm going to hold this wheel and I'm going to rotate it. And so as I rotate it, of course, you'll see it spin. But there's a blue cube and a red cube and a green cube. And so I just kind of want to focus on those as we kind of spin around here. And what we've talked about already when it comes to rotational motion is we said that there would be an angle associated with the rotation. So if you pick some point on the wheel, maybe you just pick that blue cube that I was pointing out, and as it moved, you might say it moves along some arc, it has some radius, there's some angle theta, and really kind of the best way to do this is maybe I'll start making a chart right here, and I'll say, all right, when we were working with translational motion, and how does that compare to our rotational motion? So when we were doing translational motion, we talked about like this thing X, like its position. Well, where is it? We measured it in units of meters, maybe even centimeters, maybe kilometers, but we had a bunch of different units to measure our distance. And so we can do the same thing. In fact, we already have, in the last chapter, we said, okay, the corresponding to position would be a rotation, an angle here. Okay. And so right here, then, I would say, then we could measure the angle in radians. I guess we could measure it in degrees also. Whoops, maybe I'll just put a little circle there with the degrees. We could also measure, then, in revolutions. And so all of that we've already done, so I won't add to it, but I'll just say that we could convert from radians to revolutions. And so we've done that. And I wanted to use this as a starting point, as a springboard to kind of get us started here. Because when we started doing our kinematics, we then said, at what rate does the position change? We called that a velocity. We, of course, measured that in meters per second or centimeters per second. But we can do the same thing and say, how does our angle change with time? And again, we've already done this, so I'll just, use it again as a springboard to say, in the last chapter, we looked at what it would be analogous to a translational velocity. Now we'll call it a rotational velocity or an angular velocity. And of course, we could measure that in radians per second. We could measure it in revolutions per second, or actually revolutions per minute is a little more common, so maybe I'll put those on there. But again, I know you've seen all these already, because where I want to go is then the next step, that there would be then an angular rotation to all of this. And so just like we had a translational quantity called acceleration, which now I'm going to refer to it as a translational acceleration, of course measured in units of meters per second squared, then we could put right here, how does its angular speed change with time? And maybe now you'll begin to see kind of the bigger picture here, that we will then measure our rotational quantities using the Greek alphabet and our translational ones using the Latin alphabet. And so the corresponding first letter is alpha, and so we'll call alpha the angular acceleration. And of course, the units would then be radians per second each second, which simplifies to just radians per second squared. And so all of this, I would say, is exactly what we did in chapter 2, and now we're just going to expand our chapter 2 and say instead of just translating, things can rotate. And maybe it's worth pausing here to kind of give you maybe a feel. I'll come back here and hopefully point out the obvious, but if I take the little wheel, I could go ahead and apply not a force, but a torque. Right? Remember last chapter, right? Torques make things rotate, forces make them translate. So I apply a torque, and of course now I build it up to some speed. Now if I leave it alone, if I don't apply a torque, it just keeps rotating at a constant angular speed. But if I apply a torque, so now I'll do it with some friction, it'll slow down. Its angular speed slows down. And so again, your author is going to ask you to kind of digest this pretty quickly and say, okay, remember all those things we did for translational motion? Take that same thinking and apply it to rotations. And hopefully then when I start doing some examples, you'll see that. I'll read the problem and I'll go, okay, remember how we did a problem like this back in chapter 2 for translational motion? Remember how we did those kinematic equations? Oh, let's just do the same thing, but now we're thinking about something building up speed or slowing down speed. Instead of translating, it's rotating. And of course then, we saw back here, then there is a mathematical relationship between these two. We've already seen 2 of them, and we're going to continue on. We said that the definition of an angle by the ancient Greeks was to say, take the arc length S and divide it by its radius. And so if you're looking at some point, like I said, maybe that blue cube on the end of my wheel, you could think of that, how much distance did it travel? That's the arc length. That's the S. And if you think about it in terms of a distance, you're thinking about translational motion. You're thinking about distance, the rate of the distance change, the rate at which its translational velocity changed. But you could also think about it in terms of its angle, and of course those mathematically should be connected. And so we have a mathematical connection here that says the arc length is equal to the radius times the angle. And again, this is just a good springboard to get us started because that you already saw. And in fact, we took the next step, and so actually I'll just kind of write it right here and say if you were to divide by time, or really more appropriately, if you were to take the derivative with respect to time, noting that the radius doesn't change, and so taking a derivative you can pull it out, we get the translational velocity is equal to r times the angular velocity. And so, again, this is kind of a good place to start because both of these relationships and both of these ideas of rotation we saw in our first chapter on rotation. Now we're going to kind of continue that, and like I said, there would be a mathematical relationship, a connection. And you'll see that throughout this next hour, hour and a half as we try to kind of quickly go through this chapter. And I'll do it again here. I mean, watch this. If I were to take the derivative of both sides, again, saying that the radius is a constant, so I can pull it out, I would have a nice little equation here that says A, the translational acceleration, is equal to r alpha. That would, of course, be the angular acceleration. And so the translational acceleration is then equal to this r alpha. Now, here's where I probably need to pause and say, be careful here, because acceleration can get misunderstood at this point. Because in the last chapter and the chapter before that, didn't we have, and maybe a good place to put it is over here, what we called a centripetal acceleration, which we said was v squared over r. Which we said, if you use this relationship, would be the same as r times omega squared. And the reason I want to point that out is because I have here on the board two different accelerations, if you will. Now, the total acceleration is a little bit of both, and so let me just remind you. Remember what this was? This was the acceleration needed to go in a circle at a constant speed. This was the acceleration needed to change its direction. And so if I grab a colored marker here, or what I'm really saying here is this object, which again I'm thinking in my mind as that blue little square right there, it would have an acceleration towards the center of the circle equaling v squared over r, or r omega squared, because that is the amount of acceleration it needs just to change its direction. But if it's also speeding up, then it has an acceleration in a tangential direction of r alpha. And since they're at right angles, we could then say something like, well, its total acceleration, these would be the two components. You might think of this as its x component and its y component, and we can do a Pythagorean theorem. And so you can see why I said that the acceleration here is going to be a little harder, because we've got to pause for a moment and say, are we thinking of the tangential acceleration? Or are we thinking of the centripetal acceleration? Or are we thinking of the total acceleration, which is the two combined together? And I must admit, since your author has talked so much about this chapter, and myself included, will probably talk a lot more about the translational acceleration. And so when I come over to here and I have this object that I'm going to accelerate, like I said, this blue object, as I give it a torque and the whole wheel has an angular acceleration, I'm saying that this blue square then has a tangential acceleration. And it goes faster and faster. So in other words, the tangential acceleration changes the speed of the object. The centripetal acceleration changes the direction. And that should expand our thinking a little bit. Remember when we said way at the beginning, when we got into this whole centripetal acceleration, I said, hey, if an object goes in a circle at a constant speed, does it accelerate? And hopefully got your juices flowing, and we're like, well, yeah, because the definition of acceleration is a change in velocity, and velocity has both a speed and a direction. And so now we have the tools to divide those two into the two pieces. We could look at how much and in what direction is the acceleration that changes its speed, and then how much and in what direction is the acceleration that changes its direction. And so we've got two pieces here. Now, again, I'll emphasize that your author is going to be focusing today then on this speed change. But I have noticed that students really get these two confused, because, all of a sudden we start using this and they go to do the homework and they talk about the acceleration and they jump back to this and go, well, didn't we do the acceleration? And that's why I'm taking an extra minute here to point out that we've got the two components of the acceleration. And so we'll always have to ask ourselves, when we have something moving like this, are we looking at the acceleration that changes its direction? Or are we looking at the acceleration that changes its speed? Or are we looking at both, the total, because it could be doing both at the same time, like a car getting on the freeway would go around that clover leaf, and so not only is it turning, but it's also picking up speed in order to get out of the freeway. And so this one here would help me calculate its speed increase, and this one here would help me calculate its directional, how much traction it needs from the tires to make those turns. All right, well, I hope I didn't spend too much time here, but I did want to make sure I separated out your thinking, and I think that will help as you start doing the problems. But like I said, we got a lot of material here to cover, because your author, like I said, for good and bad, says, hey, we can do rotational physics, rotational mechanics, kind of quickly, because all we need to do is say everything that we did for translational we'll do for rotation. And so like converting units revolutions to radians, I would say would be similar to converting from centimeters to meters. Talking about position, it would be an angle instead of a position, an angular speed instead of a translational speed, an angular acceleration instead of a translational acceleration. But all of those are kind of the same. And if you remember back in chapter 2, we then even did this. We said, well, what would happen in the special case that you have constant acceleration? And let me not write all the equations, but at least let me do a couple. Maybe I'll start with what we call kinematic equation number 1, right? We said, okay, if you had a problem and they asked blah, 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 this is a great equation to use if they don't give you distance and if you're not asked to solve for distance, and if it's constant acceleration. You might remember we had another equation. The second one had position in it. And we argued that this, again, was derived from constant acceleration. And so the first thing we would say is, hey, you got to have a constant acceleration. But if you have that and you are not interested in the final speed, this is a good one to use. And so if you're interested in solving for distance or initial speed or acceleration. Let me do the third one and stop. I know that there's 5 of them. Your author reminds you of 4 of them. I'll remind you of 3 of them. But of course, I gave you 5 of them. But without putting too much here on the board, because I think it'll just be too overwhelming and do more harm than good, let me put the 3 common ones and say, look, wouldn't there be equivalent to this? If we were doing a problem that started asking for something like, how far did it rotate when it started from rest and got up to some speed, given a certain angular acceleration, we would use the equivalent of this. And so here's what I'm trying to say, is as we read these problems, let me just change my thinking from translational quantities to rotational quantities. And so I'm going to encourage you, as you read the problem about these things rotating, just kind of in your mind, go back to chapter 2 and go, okay, now how would I do this problem if it was a translational problem? And you're going to see it's very similar. Instead of the ball being thrown up and coming to a stop, the disc is spinning and coming to a stop. And this one would take a while to come to a stop. But it does have some friction here. But it's going to spin for quite a while. And so there is a acceleration. Maybe you call it a negative acceleration or de-acceleration, just like the ball going up. And so I would put then, to kind of help you here, the 3 most common, and we can even put the 4th and the 5th, but like I said, I have just about enough room here to kind of give you the main thrust of this argument. And that is, if you change all of your translational quantities into rotational quantities, and you convert your thinking from translational motion to rotational motion, we should be able to do problems involving things rotating, just like we did problems with things translating. And I know I've said that quite a few times, and I'm going to keep saying it. I'm going to keep saying it over and over again, because it's easy to say in words, it's easy to hear, but I must admit, it is a little challenging to do that. You read the problem and go, ooh, how do I do this? But it really does help if you then pause and say, well, maybe I should think of it like back in chapter 2 when it was a translational problem. And think about what you would have done there. And then that will help you then to do the rotational piece. Anyways, like I said, I'm gonna stop there because I want to continue this chart and show you that, hey, this whole idea of continuing to think about our mechanics, and in this case we're going to do a rotational mechanics, we can continue to just say, okay, what would I have done in this same scenario if it was translational problem instead of a rotational problem? And here's why I say that. Because, like I said, good news and bad news is that if you recall, we did all of this stuff right here over the spread of 2 chapters. From your author's perspective, we'll just call that 1 or 2 sections of this new chapter, and then go on to things like dynamics. Now, we spent 3 chapters, chapters 4, 5, and 6, on Newton's second law, forces and translational acceleration. Any guesses what we might want to replace here? Instead of force, we would have torque. Instead of translational acceleration, we'll have angular acceleration. Instead of mass, we'll have... Ooh. All right, well, maybe we better have a discussion here. All right, so let's pretend we're back to chapter 4 for a moment. Let me take the ball on the end of a string or anything that is then at some distance away, and I'm going to push on it. And of course, this push would make it go in a circle. Now, if we were in chapter 4, I would have thought of this as translational motion, right? I would have said, okay, I'm going to apply a force, and then that's going to result in an acceleration. I'll keep it simple and say the net force, but it really, for our discussion, there's only going to be one force on it. I'm going to just kind of push it with my hand. Okay, so there's that force F. So I could write something out here. Let me give a certain radius to this, and so it looks something like this, and I push it. But let me take advantage of what we were just talking about here. There's a mathematical connection between its translational motion and its angular motion. So if I wanted to kind of look at this a little different, I would say, let's think about this thing not translating but rotating. And of course that means it would move something like to here, and so it would rotate through an angle. And of course, then we would have an angular speed and of course an angular acceleration. And that's why I put this here. All right, now, let me take another step. Let me multiply by another r. Now, in case you're wondering why, do you see what I get on this side of the equation? This is the torque we were talking about. Remember the last chapter, we spent quite a while trying to emphasize that when you make something rotate, it needs not just a force, but a torque. And remember, a torque was more complicated. A torque depended upon the amount of force, the position you applied the force, and even the angle that you applied it. Now, I made it a little bit simpler here by saying, let's just apply the force in the direction we're moving, but I could have put a sine theta in here just to make sure that I'm talking about the component of the force that is along the tangential of the circle. And that would have made it a little better, so maybe I'll throw it in here afterwards. But what I really wanted you to see here is I have my first step towards dynamics, my first step towards Newton's second law. I would call this Newton's second law of rotation. And so instead of having a connection between translational quantities, I have a relationship between rotational quantities. This is saying if you apply a torque, you will then end up with an angular acceleration. But you have this other factor here that is more than mass. It is actually the mass and then the radius squared. And let's pause here and take a look at how we might interpret that, because we're going to then refer to this as its rotational inertia. Sometimes we use the mathematical term moments of inertia. And so I noticed your author starts off by calling it rotational inertia, and then a little bit later he uses the mathematical term moment of inertia. So I thought I'd just give you a little warning. Don't, you know, they're talking about the same thing here. But what your author is trying to say here is this quantity together, not just the mass, but the mass and the distance represent a resistance to motion. Again, let's go back to chapter 4. In chapter 4, we said this: acceleration is force over mass. And we said that there are a part of this equation that makes the object accelerate. That's the push. And so there is the numerator, force. And so you put a force on, say, a car, and it begins to accelerate. But what is opposing the car from accelerating? And I'm not talking about other forces like friction. It was this mass down here. That's why, if you remember back and forth, I kind of imagined myself here on the stage and say, so what if I push a bike and I push a car the same amount? Do I get the same result? Do I get the same acceleration? And the answer was no, because it's not just how much you push the car, but it is also how much inertia, how much mass does it have. It's harder to move that car just because there's more material there. There's more mass there. And I'm trying to give you that same gut feeling that we're going to call this rotational inertia. We're going to use that phrase inertia because this number right here, which let's go ahead and use the symbol I for rotational inertia. But that means Newton's second law for rotation would look something like this. And maybe I will put a box around it, and I wish I had given myself maybe more room here. Oh, I know, I could probably squeeze it right here. I think there's kind of enough room if I don't write too big to say, all right, here is the idea of translational motion. Here is our new idea with rotational motion. And we had F equals ma. Now we have torque equals inertia, rotational inertia, times angular acceleration. In fact, let me write this equation like I did here. I would say the angular acceleration depends upon how much torque and how much rotational inertia or moment of inertia does this object have. And so, besides showing you here Newton's second law, I hope I'm also getting into your mind this whole thing about inertia. In other words, making something rotate has resistance because of something that's more complicated. And so remember, I've been saying that torque was more than force? I'm going to say the same thing. Rotational inertia is more than just plain inertia. It's more than just mass. It's mass and then the distance squared. Where is it? In fact, all of these are worth putting in the chart then. So forces are equivalent to torques, and mass is equivalent to rotational or moment of inertia. And so when you thought about making something translate, You go, oh, give it a force. Now I'm going to say you want to get something to rotate, give it a torque. And then you say, okay, well, what makes it hard? What opposes something from translation? You would say, oh, it's mass. How much mass does it have? Okay, fine. Now I'm going to say, what makes it hard to get it to rotate? And I'm going to say, oh, it's rotational inertia. But I'm also going to say, just like torque is more than force, rotational inertia is more than regular inertia. It has a mass and what I like to call the position of that mass, how the mass is distributed. And so if I just took something like this 1 kilogram and I say, all right, I'm going to get this 1 kilogram to rotate. So I'm going to go over here. Maybe I'll even change it from rotating clockwise to counterclockwise, clockwise to counterclockwise. So in other words, I've got to speed it up, slow it down, speed it up, slow it down, speed it up, slow it down. I got to keep changing its angular speed. Now, how difficult is that? And I would say it has some resistance. It has some rotational inertia. And if I put my arm out here and do the same thing, it is harder to stop and get it going than if it is in here. This is easy. This is more challenging. It has more rotational inertia. So you can see here that, and I'll say it again, rotational inertia is more than inertia, torque is more than force, and we have the same principle of Newton's second law, it's just a bit more complicated. And so we've got to take our thinking from translational to rotation, but we also have to remember that idea. In fact, it's worth then mentioning the units here. And so coming over to force, we said force was in newtons, but over here the torque is a newton times a meter. When it came to translational motion, we said the units here were kilograms. Ow, what's this new crazy thing? What would the units here be? And I'll say it again. Can you kind of see it's made up of more than just inertia? It has kilogram, but it also has distance squared. And so the units here are kilogram meter squared. Yeah.
So why when we were trying to open the door, it was easier when we had more distance from center?
Oh, okay, good point. Because, okay, so, okay, all right. So the torque is the force, and that R is where did I apply the force. Don't confuse that with this M and this R squared. I know this has an R in it, okay? But these are different R's. These are different meanings. So you guys online, she's asking, how come when I push on the door here, it was better to go further out? And I would say because my force is being applied at a greater distance. That's what I'm doing. It's this distance. I'm applying a greater torque. See, what is this? This R is not the position of the force. This is the position of where the mass is. So if you were to, and let me come back to this weight, give you an illustration. If I were to come over here and say, okay, I'm going to open this door. Okay, where I apply the force. So my hand, the R is from the pivot over here to my hand. That would be this R right here. This is where am I applying the torque. But then getting the door to open, the resistance to getting the door is the mass of the door. And so where is the mass located? So if I were to put this right here, that would make it easier to open the door than if I were to put the mass out here. And so this is the R of where is the mass, not where is the force. Good point. And I can see now by your question how it'd be so easy to confuse these R's. But this is the R of where the mass is. And in fact, I thank you for asking that, because in this simple scenario, they were one and the same. I had just one little point mass. The position of that mass was actually the same place I was applying the force. But that may not be the case, and your door illustration is a good example of that. I could put the weight here, and so this is the distance of the mass, but I could put my hand here, and so this is the distance for my torque. And so those are different R's. And good, because that's the next thing I want to show you. That's where this gets really complicated. But I thought I'd also take a moment then to have a fun little experiment, and even to invite you guys on the break or after class, if you want to try these, we call them the inertia rods, because they're designed to help the students kind of get a better feel for rotational inertia. They actually have the same amount of lead shot. So we put them in these plastic tubes, and you might even be able to see there's just a bunch of lead little tiny ball bearings in there, and we've got them capped with some pieces of wood here. In this rod, we've separated it into two and moved the weights out a little further. But the total amount of mass is the same. And so if you were translating these, if you gave it a push, and this one the same push, you would end up with the same translational motion. They have the same mass. However, if you go to rotate these, they're very different. And so this one here, when I go to apply a torque, and I'll use my wrist for applying the torque, and so I'm going to rotate about the middle of my wrist, and so kind of maybe most of it will be right here, my thumb and my index finger, and so I'm going to push it this way and then stop it, and then push it this way and stop it, and just kind of go back and forth and go, okay, I can start, stop, start, stop, start, stop. And that's actually pretty easy. I'm applying a certain torque, and its resistance is the inertia, rotational inertia, which isn't just the mass, but where it's located. And see how the mass is located what I would call a short distance from the pivot point. Here, again, here's about the pivot point, my wrist. Now, some of the mass is out a little bit further than others of it, but all the mass is kind of close in. And so I would say overall, this has a small moment of inertia and actually rotates back and forth pretty easy for a certain applied torque. Now, assuming I'm not tired from all that, I could probably apply the same amount of torque, let me find the middle, to this. And so as I go to start, stop, start, stop, start, stop, it is a lot more struggle to get it to move. I'm probably even applying more torque, because I'm just like, oh, I've got to push this. And you can see the effect is a lot less. I'm having a hard time making it start and stop. And the reason being here is because even though it's the same mass, it's the location of this mass. This mass is way out here. And then back to your question, don't confuse, the torque is coming from the force of my hand, so it's this distance. But the moment of inertia is this distance, where the mass actually is. And so what we refer to the distribution of the mass comes into play. And I would say if there's anything that is the hardest of rotation, it's right here. It is trying to convince students that rotational inertia is more than regular inertia. And it depends then on where that mass is distributed. And the best analogy I can give you is just like torque is more than force, rotational inertia is more than just regular inertia. It's where is that mass located? Yeah.
Where would the R be if you pick it up again?
Oh yeah.
What would your R distance be?
Okay, now I want to be careful. I think you're talking about the R for the rotational inertia, not the R for the torque.
Yeah.
Okay. So it's pivoting maybe right about, the middle of my wrist right here. Okay. So R is the distance from the pivot to where the mass is. Now, here's where it's going to get a little more complicated. I don't just have one chunk of mass. I got a bunch of BBs in here. And so these BBs are a little closer, but they're still kind of far. Then these are even further, and these are further, and these are further, and these are further. And so the next and tough thing to understand is then to say, if you wanted to know the total rotational inertia of something, you need to take, say, the mass of some little piece, usually we call it the ith piece, if you kind of remember our calculus, and then the position of the ith piece, and then you add it up. I will say this, we're not going to bother to actually do the mathematics to add this up. I will just say that I think you can kind of get from that if you added all these up, because this is the small r and this is the big R, would come out to be a bigger number than if you just started here in the middle and this is the little r and then this is the big R. And if you added all these up. Just because the r's are different. Now, here's why that's important. Let's take two objects right here and ask a conceptual question with this. You probably can't tell from your distance, but again, on the break for you in-class people, and I'll just tell you online people, these have the same mass. They even have the same radius. They even have the same color, if that matters. But to get them to spin, will it take the same effort? Does this one spin easy or harder than this one? Right. Good point. Let me draw a circle here and go through maybe a little picture here. But if I was trying to figure out the rotational inertia, and like I said, we won't take the time to actually do the calculation, but I do want you to get a gut feel and a conceptual feel for this, and you'll be able to tell by looking at not just the mass, but the distribution of the mass, which one would be of a bigger or smaller moment of inertia. So on this one, we purposely gave them the same radius, we purposely gave them the same mass. So this one's made out of metal and this one's made out of a light wood. Purposely gave them the same mass, the same radius, but yet one is solid disk and one is what we'd call a ring or a hoop. And if you look at the two, and so maybe I'll go here, let's look at a disk, and let's look at a ring. The disk and ring, you might say, okay, look something like this. But the ring has all of its mass on its circumference, whereas the disk has its mass distributed out from the center all the way out to the circumference. And so maybe it'll stand out if I took a different color here. But if I wanted to know the rotational inertia of this ring, I guess I would take maybe a small little piece and then add that to another small little piece and add that to another small little piece. And that equation I just erased said, okay, the total inertia of this thing would be to add up all the pieces. Now, again, let me not go through the calculation, although this one would be fairly easy, so I think it wouldn't take us long. But I do want you to see that wouldn't every little piece of mass be at the maximum radius of the ring? But over here, we've got a different picture. Over here, there would be chunks of mass that would be at the full radius, sure. But there would be, I'll put a center there, there'll be other chunks of mass that are closer in. And so I'll just draw a few of them. And say if I was trying to get the total inertia of a solid disk, I would add up this mr squared. And again, without actually doing the calculation, I'm hoping you could see that when you start doing the disk, some of the mass is not at the radius of the disk. Maybe to make it stand out, let me call this a capital R. And point out then that this R represents the radius of where the mass is. It doesn't represent the radius of the disk. It represents where is the mass. And some of the mass is out on the perimeter or circumference. Don't tell your math teacher I said perimeter. Okay, circumference. So some of it's out there on the circumference, but most of it is not. Whereas something like this, all of it is at the circumference. And so I claim because of that, this one is going to have a larger moment of inertia than this one. Meaning this is the one that's harder to get going than this one. Again, notice they have the same mass. Notice they have the same radius. Now, like I said, I won't go through the detailed calculations, but I will show you a little chart that we're going to use a lot in these problems that does the calculations for us. And so if we're working on a problem and we have something in the shape of a ring, the moment of inertia actually comes out to be just the mass of the whole ring times the radius of the ring squared. But for the disk, it is something less than that. And it comes out with a factor of 1/2 in it. Which maybe kind of makes sense because the 1/2 would be saying kind of an average. In other words, some of the mass is greater than half the radius and some of the mass is less than half the radius. But again, I just want to emphasize that they wouldn't be the same number. And you can kind of see then, from a conceptual point of view, which one would be bigger and which one would be smaller. To kind of illustrate this, let's have a race. Let's race them down the hill. See, if everything I told you is correct, I'm saying this one is a little bit easier to rotate. So if I put it on the hill and let gravity rotate it, I guess I'm claiming that this one would rotate easier than this one. They're both going to rotate, but let's see which one rotates faster. And so I will start them together and let them race. 1, 2, 3, go. And I hope you see this one won. This is my little experiment to say, yes, one of them rotates faster or easier than the other. Which is why I kind of left the display up here, because your author then talks about all of these relationships and does the kinematics. And then he gets into this dynamics that I was just talking about. Where is it? Here we go, section 3. And he goes to this little derivation. And then he gets to this table. And he says, the same thing I'm going to say here. This can get really complicated trying to add up all these little pieces. And that really takes us beyond the scope of this class. So we're not going to make you add them up. We'll save that for the engineers class, and they got to figure out all these shapes and add them up. What you want to understand is things like, a straight arm going out here, how hard is it to get it to rotate? Well, then I could maybe kind of look at this right here. I can kind of think of this arm as being a rod of length L. And so if I take the length of my arm and I say, okay, how hard or how easy is it to pivot it around my shoulder here, I could take the mass of my arm, and it looks like the length of my arm squared divided by 3. Because this says a thin rod about an axis through one end that is perpendicular. Of course, not to be confused with this one over here. This says, what if you have a thin rod that it is rotating around the middle point of it? And so, I guess I can't really do that with my shoulder. I'll go back over here to the rod. And maybe this isn't a fair description because this does not have the weight evenly distributed on it. But that's what this one is talking about. It says if you have something like this and you're going to rotate it around its center, use the mass of the rod, then the length of the rod squared, and divide by 12. Because all of these are kind of close. But if you're rotating around its end, well, divide by 1/3. And of course, if it was all the way at the end, if all the mass was at one end, then that's the easy one. That's just mr squared. That's just one object. That's how we got started with this discussion. We weren't looking at it as a bunch of summation of a bunch of pieces. And so if you've got just one object, just go mr squared. And again, the r is where the mass is located. Of course, your author does a good job of looking at other ones. Here's the one I just mentioned. Here is the hoop or the ring, and that's what I said, right? mr squared. And so if I wanted to know the inertia of this one, it's just mr squared. But the disk should be the 1/2. Where is the disk? Maybe it's further down here. It's actually right here. He kind of shows a cylinder. Usually we think of a cylinder as it's longer than its diameter, but I think you'll see that a cylinder and a disc are really kind of the same thing. A disc is kind of a short, fat cylinder. Okay, so here is his cylinder, and then he says, or disc, and so there it is. There's the 1/2 mr squared I was talking about. This is just a long way of saying you're going to need this table a lot. They're going to talk about rotating maybe a human, and they'll say something in the problem. Okay, think about a human as a cylinder, and so you're going to use this 1/2 mr squared. Or maybe they'll say rotate a human with their arms out, and so you'll go, okay, so my human is a cylinder, so I'll use the 1/2 mr squared, and then it's a cylinder plus a rod. And so then I'll use that 1/3 ml squared. And then I'll add another rod, so another ml squared for that cylinder. And I'll rotate them. And I'll figure, okay, that's the inertia to get this to rotate. And so if somebody comes along and says, all right, here's what we're going to do, is we're going to ask this question. We're going to say, what is the acceleration of this human? If somebody is standing on a platform, they're on here, they've got their arms out, and somebody comes and pushes on their palm, well, we need to know how much torque is being applied to that person. So we've got the force on their palm and the distance, so that's how we get the torque. Then we divide that by the inertia of this cylinder with rods, and then that would give us the angular acceleration. And so just like in chapter 4, we did force divided by mass, we will now do torque divided by rotational inertia. But that rotational inertia in itself is a hard problem. Just getting the rotational inertia of a whole human. Yeah.
So why is the proof about any diameter kind of has regular radius axis? You see that on the
Oh, are you looking down here?
Yeah.
Okay, so this one up here, and can you see the green line? So this is saying if you were to rotate it around this axis, okay, so I'm going to spin it like this. If you change it to this, you're spinning around a different axis. And in this case, as you are pointing out, it's a smaller number because here, as you spin, most of the mass is not all the way at the full radius of rotation. See, this mass up here is closer in. When I had it in this configuration and rotated, all the mass was at what I call the full radius of it. And so this one comes out to be a little bigger. Actually, I'm glad you pointed that one out because I'll do something like this. You'll get questions about balls rolling down the hill or spinning. And so is it hollow? So a racquetball is hollow, or is it solid? You see, when it rotates, if it's solid, then there's a lot of mass that is not rotating around what I call the full axis. But if it's hollow, then you've got the mass, and a lot of the mass outside where it rotates. But even then, it's not all at the full axis because this shape is a lot like this one that you just mentioned, where it rotates over. And so you'll see that they give you two spheres, and they say, all right, if it is solid, it's 2/5 mr squared. But if it is a shell, or it's hollow inside, it's 2/3. So this one's bigger. 2/3 is bigger than 2/5, right? 2/5 is 0.4, 2/3 is 0.66. So this is, 50% bigger than that. It's quite a bit harder to get a ball with a shell to rotate than one that is solid. Okay. Although on the other hand, let me also be very, very careful in this because a factor that is hopefully obvious, but I'm just kind of going real quick, is how much mass does it have? So when I did these, I made it very clear these have the same mass. Clearly, if one just had more mass than the other, that would be harder to rotate. And so when you take a ball and you cut out the middle, you're actually giving it less mass than if it was solid. So I'm not comparing a ball that's solid of the same density to a ball that's hollow of the same density. I'm comparing them to same masses, which means they got to have different materials to get that same mass if you don't have less material. So again, you can see how this could get pretty complicated here. And you can see that I decided that this is where we should spend the majority of our time on the chapter here, is really right here, dynamics. For everything we did for translation, we'll also do with rotation, but we're saying it again, torque is more than force. And rotational inertia is more than just simple regular inertia. And this will be the challenging one. Except for the fact it's so challenging that we'll just give you a picture and say, look it up on the diagram there. And so maybe that'll be the good news here. Well, I'll keep going here and say, all right, what else did we do in these chapters? Well, you might remember that after we spent 3 chapters on Newton's laws of motion, we then went into the conservational principles. And we had conservation of energy, and then we had conservation of momentum. Let's repeat that discussion here. And so let me put up here kinetic energy. Let me point out that we said, and see if I get the chapter right, I think it was chapter 7, we said that an object, moving along has kinetic energy. It's equal to 1/2 mv squared. That was the good news of chapter 7, that I said I would go through those integrals for you, and you wouldn't have to do them again. And then we could just say the energy you start with is equal to the energy you end with. And one side of that equation came out to be that 1/2 mv squared. But what about something that was rotating? What if it had an angular speed omega? I hope you kind of see that this would have a kinetic energy too, right? Isn't it moving? Isn't it have motion? Now it's going in a circle instead of translating. And in fact, again, you can kind of see where this gets a little more complicated, because wouldn't a point like right here that is close in and one close out be moving at same speed or different speed? Well, let me come back to this wheel. I think you'll see that I have a blue cube, a red cube, and a green cube. And I'll spin it. Are they moving at the same speed? And I will say it's a loaded question. Because is it the same translational speed or is it the same rotational speed? And I would say it's the same rotational speed, but different translational speed. Right? Let's say it takes 1 second to go around. Say 1/1000. So I would say all of these make a 2 pi radians in 1 second. All of them have an angular speed of 2 pi radians per second. However, coming back to our discussion earlier, it's still right here on the board. Notice that the translational speed depends upon not only just its angular speed, but where it's located, where the R is. And so coming back over here to this picture, I would say the one that is close in is going slow in terms of translational, and the one on the outside is going fast in terms of translational. So I'll say it again. They have the same rotational speed, but different translational speeds. So if I were to ask this question, what is the kinetic energy of rotation? And this then would be the kinetic energy of translation. I hope you're kind of seeing that all I would have to do is add up the kinetic energy of translation. But I'm hoping you'd also see that might be kind of hard to do because they're all going at a different speed. But luckily, we kind of covered this. If I would add them up, I would put 1/2 mv squared. But remember, the v is r omega. And so if I were to say I'm going to add up a bunch of pieces, and I may start my conversation saying I'm going to add up all their translational energy, but when I do this step, I'm going to stop thinking about them as a translational speed and start putting them as a rotational speed. I would even say there's no point in putting a sub I with the rotational speed. They all have the same rotational speed. Oh, I'm sorry, I forgot a square. Well, my speed squared, I needed to square both the radius and the speed. But here's the good news. Watch this. Every term has a 1/2 in it. Every term has an omega squared in it. This thing in the middle would be the sum of mi/ri squared. Doesn't that look familiar? What would this be? This would be the rotational inertia, or the moment of inertia that we've just been talking about. And so it means I could write this as 1/2 I omega squared. And it's kind of nice. It makes it kind of easy to memorize, doesn't it? Because don't you already know that the translational kinetic energy is 1/2 mv squared? So the equivalent of m is the I, and the equivalent of v is the omega. And so let me add this to the chart over here. We could have a 1/2 mv squared if we were thinking about a problem with conservation of energy, and we looked at its translational energy. Now we could do a problem and talk about 1/2 I omega squared. And we could do a problem using conservation of energy. But again, instead of using m for mass, we would use I for inertia. Instead of using v for translational speed, we would use omega for angular. Now, maybe another example would be helpful here. Why don't I go back to this rolling down the hill piece? Let me do this. Let's say that I have a situation where something is on top of a hill. So I'll give a little hill, a little incline. Let's just say we start at some height h, or maybe I'll just say y initial. Let me not give a shape or anything to my object at the top. Let me just go, I have an object at the top. It has a mass of m. Now it's got to have a shape to roll down the hill. And I want to have a little discussion here with you to maybe help you understand, what if that object going down the hill doesn't rotate at all? And I know there's wheels on here, but most of this doesn't rotate. The wheels are just here so that I don't have to battle friction. All right. So what I'm really trying to do is, what if I were to slide something down without friction? But I want you to see, I'm going to race this down the hill, and it doesn't rotate. But this one does rotate. This one here also rotates. So it could be any of these three objects I'm thinking about as they go down the hill. But if I was doing the principle of conservation of energy, let me pause again. Here's the good and the bad of this chapter, right? What I'm trying to do is now do chapter 7. I told you. The good news here is, hopefully you see the analogy. Everything I'm doing here for rotation, we've already done for translation. Bad news. That means we're going to try to do all these chapters, right? We did chapter 2, chapter 3, chapter 4, chapter 5, chapter 6, and now I'm into chapter 7, and we're about to do chapter 8 before we call this chapter done. So we're going to do everything we did for translational motion for rotational motion. So you might remember doing these problems in chapter 8 with conservation of energy, or maybe I should say you're kind of working on those now. That's probably where you guys are working on the homework. You already saw the lecture, you already did the lab on it, but you're getting ready for, an exam. Don't panic yet. Still 7 days away. Plenty of time if you start working towards it now. Don't wait till Sunday night. But we did the principle of conservation of energy. And if you remember doing that chapter, we did something like this. We said the initial kinetic energy plus the initial potential energies plus the work done by the non-conservative force goes into the final kinetic energy or into the final potential energy. And then when we spread this out, we said, well, kinetic energy would be 1/2 mv initial squared. And if you remember then, potential energy, we said we came in two flavors. We had a potential energy that was based on gravity, so we called it gravitational potential energy. And then we had a potential energy that had to do with that spring, that elastic. And so we had this mgy initial and a 1/2 kx initial squared. I'll just leave the non-conservative one alone, but if it was friction, we said it was this. We said it was negative force of friction times distance traveled. And so this is all the energies you start with, and then minus the friction or the heat you're going to create. And then on the other side, you're going to have a 1/2 mv final squared plus mgy final plus 1/2 kx final squared. Now, again, maybe I'm spending too much time here. This is kind of maybe to help you as you're still working in Chapter 8, because many of our problems, most of our problems don't have every piece involved. But here's the big picture I want to say. And to make it stand out, I'm going to change colors. Just like we had two potential energies, now we're going to have two kinetic energies. See, an object can be translating and rotating. And so there needs to be a term added on both sides of this equation for our second kinetic energy. And so something like this disc rolling down the hill, when it gets down here at the bottom of the hill, I will say this disc is not just translating, but it is also rotating. And so for the principle of conservation of energy to work, I got to include all the energies. And when we first did it, we were exposed to quite a few energies, but not all the energies. I mean, notice up there, we don't have solar energy in there. We don't have chemical energy in there. And there's a lot of energies that need to be added for that to be a true statement. We just did enough to get us started, and a big one that we didn't have was rotation, and now I'm trying to add that in. We'll talk about electrical energy in next semester, and we'll add that one in there. We'll have magnetic energy. We'll add that one in there. We'll have solar energy next semester. We'll add that one in there. And so this formula is going to build. Unfortunately, not all the energies are involved in any one given problem. But here's what I want to do then. I want to go ahead then and take this general principle of conservation of energy and emphasize to you, now you have to add rotational ones, and let's apply it to this problem up here. So I'll say it again. Here's my problem. I got something up at the top, and then I just let it go. So when I take it up to the top here, I'll say there's a 0 kinetic energy for translation and a 0 for rotation. There's no springs, and I'm going to say it rolls without slipping, so there's no friction. The end of the story is I just have an mg, and I don't know if you want to call it an h like your author does, or a y initial like I've been recently. But I would say that if I think about the principle of conservation of energy, up at the top of the hill, there's only one energy that it has, and that's gravitational potential energy. Now it rolls down to the bottom of the hill. Where does it go? Well, I would say we no longer have this term. We no longer have gravitational potential energy. We never had a spring, so I won't worry about that. But I would say that this has then some of its energy as translational and some of it as rotational. And here's why I bring all that up. Do you remember when I got started here, I said one object doesn't rotate at all, this one. So as this one goes down the hill, I would say all of its potential energy becomes translational kinetic energy. Oh, let me just say 10. If I start with 10 joules here of potential energy, then when it gets down here, it has 10 joules of kinetic, translational kinetic. Here's why that's important. What if I take a different object, one that rotates? It may still start with 10 up here. When it gets down to here, I want you to see that the 10 is now distributed, some of it into translation and some of it into kinetic. Kinetic of rotation. Let me say that again. So some of it is translational kinetic energy and some of it is rotational kinetic energy. Just for the sake of argument, let's say 7 joules are translational kinetic energy. Because this thing has to rotate and some of its energy has to go to rotational kinetic energy, it cannot have as much as this one in translational kinetic energy. So I hope that would tell you, if I had a race, which one would win. They're both starting with 10. But this one is going to put all of its energy into translation and therefore have a greater translational speed. This one's got to give some of it to rotation, so it has less for translation. And so clearly then, if I let it go, this one wins by a lot. And of course, you already told me and saw that this one beats this one. So clearly this one must really beat this one. Let's keep going with this calculation. So if I did something like this, 1/2 mv squared plus 1/2 I, and let me come over here. Remember, is there a mathematical connection between the translational speed and its rotational speed? I could then write this as v squared over r. And if I were then to factor out a 1/2 and factor out a v squared, I would have a m plus I over, I forgot a square again, r squared. And if I was asking this question, how fast is it going at the bottom of the hill, I could then move this to the other side. So I'll start by first moving the 2 to the other side. So I'll bring the 2 over. Then I'll divide by m plus I over r squared. And then that would equal to v squared. And I guess now if I take the square root, I get v. But something we already saw earlier, but it's worth repeating, wouldn't the object with the biggest moment of inertia, see how it's down in the denominator? The object with the biggest moment of inertia is going to be the one that has the lowest speed. And so sure enough, I'll show it again, you already saw it, but this one here has a bigger moment of inertia than this one. And I did it in terms of Newton's second law, but now I'm going to show you again in terms of energy that as they roll down the hill, they will not be going the same translational speed. This one has a bigger translational speed than this one. And that's because this one has a bigger moment of inertia, and therefore it takes more energy to rotate it. So a bigger percentage of its energy is tied up in rotation, so it doesn't have much money left over. I was thinking of a good analogy would be, look, if you had $100 to your name, but you had to pay $75 for a particular bill, you're only left with $25. But if this person had the same $100, but their bill's only $50, they have more left over for and in this case, translational motion. And so in terms of energy and in terms of money, we could say which one would be going faster. And so the energy has to be distributed out. And that's what this little equation is trying to say. Well, it's probably a good time for a break. We've got really one more thing. I was kind of hoping to get this in there before the break, but if you remember then, we did chapter 9, which was on the momentum and the conservation of momentum. No, that was 8. Yeah, 8. But anyways, let's talk about that same thing when we come back for the break. Conservation of an angular momentum. All right, well, we'll see you in 15. All right. Hey, welcome back here. Let's now that we've had our break, let's wrap up this chapter. Maybe I'll do a few calculations. Or maybe I'll add those as a supplement. Maybe that would be a better approach here. But there's a few more things. Like I said, there's good and bad about this chapter. The good part is everything we've done in the past, we're just repeating. The bad part, though, is that's the way your author views it, and so your author just gives you tons of material. Everything we've done from chapter 2 through chapter 8, he just kind of throws out there and says, all right, let's repeat it. So we have one more thing to talk about, and that's terms of momentum, but before we even do that, I thought I would take advantage of your author's picture here, and so on the break here, I went out and grabbed the tennis racket. For that matter, I even grabbed a baseball bat here. All right, so whether it is a tennis racket or a baseball bat or a golf club, a good example of kind of keeping track of both translational and rotational motion in your mind is hitting a ball, hitting a tennis ball, hitting a baseball, hitting a softball, hitting a golf ball. And so your author illustrates it here with a tennis racket. And then he goes, okay, in this first picture, if you had a tennis racket and you go to hit the tennis ball, the ball is going to put a force on the racket. So looking at this object, it will have both a force and a torque. Thinking of both translational and rotation, the impact right here, and let's just talk about translation, it'll apply a force, and that will tend to move the racket backwards. But if you look at its center of mass, which if I try to balance it, it must be right about there. So the center of mass of the tennis racket is right here. Notice you don't try to hit the tennis ball at the center of mass. There's what they call a sweet spot. Because as you hit it, as I said, there will be a force from the ball pushing it back. But if you hit it just past the center of mass, there will be a torque that will rotate it. Now take a look at the handle where I'm holding it. I've got two things going on at the same time. I've got the impact pushing it back, but I've got the torque rotating it forward. What if those two just matched? So that the force of the impact pushing the handle back and the impact creating a torque around the center of mass pushing the handle forward are exactly balanced. What would that feel like in my hand then? So I go to make an impact, and the handle doesn't seem to want to go back or forward. Doesn't it just feel like I hit the ball and it just feels easy to my hand? There's no force in my hand having to push it forward, but there's no impact on my hand kind of holding it back. It's a perfect balance. And that's what your author's trying to get at there. What we call the sweet spot on a tennis racket or a baseball bat or a golf club is he's trying to illustrate right here that if you hit the ball too far forward, you get more rotation, and so the handle goes more forward than back. And so the player's got to hang on to that, and they feel that impact, and they go, oh, I got to hold that tight. Here, if you get more of a backward motion than a rotation, then you feel that backwards push. But if you get it just right, and you make an impact at the sweet spot, we call it, from a science point of view, the center of percussion. It has a perfect balance. You see the same thing with a baseball bat. I purposely put some red tape here to illustrate that this is the center of mass. This is where the bat balances. That's not the good spot to hit the baseball. This is the center of percussion. This is the sweet spot. This is where, as you came around, if the ball were to hit right here, the translational motion moving the bat back and the rotational motion moving the handle forward and the head backwards is exactly matched. And so you go through and your hands don't feel a big thud backwards or a pull forward, which of course you hopefully would overcome with the strength of it, but you would just get a nice swing and a nice feel on your hands as you hit the sweet spot. And so if you've ever played any of these impact sports where you, like I said, hit a baseball, hit a softball, hit a tennis ball, hit a golf ball, is that it? What else do you hit with? But there is that magical spot. And you just know when you hit that sweet spot. It just feels right on in your hand. And so this, I think, is a good illustration of a common experience where you could say, okay, I see how both translation and rotation are happening at the same time. And I need to think about both of those at the same time. All right, well, like I said, one last thing on rotation, and that is momentum. We're going to call it angular momentum, or sometimes just rotational momentum. I'll bring up the picture of an ice skater here, because we had, if you remember, this principle of conservation of momentum. I'm going to now call this conservation of linear momentum, because this will be our third and final conservational principle related to mechanics. As I said, this is our final chapter on mechanics. And so we will solve problems using rotations just like we did for translation. And I'll try to give you some illustrations here, but let me start with kind of this picture again. Here I have a circle. Maybe it's the ball at the end of the rope again, and it's moving along. And if I start with saying it's linear momentum, P is equal to mv, let's play the same game with linear momentum that we played with kinetic energy. And that is, let's change the velocity from a translational velocity to an angular velocity. So we'd have that extra factor of r. I erased it on the break, but that was that little chart we had right here. We can go from translational velocity to rotational velocity. And let's take advantage of the fact that if we multiplied both sides by r, on this side of the equation, we would get something that is this rotational inertia, this I, times this omega. And that could be extremely useful. I'll put it in the comparison chart over here, right? We had, for translational motion, mv is equal to linear momentum. And to help with the analogy, in place of m, I'll put I, and in place of v, I'll put omega. And so I would argue here that this is something interesting. And this is what we're going to give a symbol L for, and we're going to call it then the angular momentum. And I'm going to use that same phrase. Notice that angular momentum is more than just momentum. Notice it has the linear momentum and then multiplied by r. And we've seen that a lot. We said torque was more than force. We said rotational inertia was more than regular inertia. And now I'm going to say that angular momentum is a nice quantity, and it'll have a conservational principle, but angular momentum is more than just linear momentum. It is linear momentum times that extra distance r. Maybe it's worth putting the units up here. And I guess we could do that in both directions. I guess over here on the left-hand side, I would say, what were the units for linear momentum? Kilogram meter per second. So if I multiply by an extra distance, I will get a meter squared. And so kilogram meter squared over second is the units for angular momentum. I guess if we do it on the other side of the equation, this will give me a chance to remind you before the break. We said, what are the units for this new quantity called rotational inertia or moment of inertia? It's kilogram times meter squared. What is the units for angular speed? We said radians per second. This might be a good time to go back a chapter and say, okay, remember then that radians wasn't a real unit. Maybe I should emphasize that. Remember the definition of a radian from the ancient Greeks is an arc length over a radius. They're both lengths. They're unitless. We only call them radians just for our own clarification. We just want to say, hey, this is an angle of 2 pi. We often say 2 pi radians just for clarification, but it's not a real unit. So let me just drop it out. Since it's not a unit, it's just a clarification. And in this case, I think it just doesn't clarify anything. It makes it more complicated because I want this to show you that it matches that. And so there's our units. And so coming over here, I could say then the units would be kilogram times meter per second for translational momentum. But for angular momentum, it's kilogram and then has a meter squared over seconds. And of course, I didn't put the unit for energy. I guess I just thought it was kind of obvious, but I'll say it again. All energies are measured in joules. So they come out to be joules where we're talking about translational or rotational kinetic energy. Now, again, why is that useful? Well, let's come back to chapter 8. Remember, you might remember a problem like this. I had these carts up here, and I said, okay, let's take cart number 2 and have it collide into cart number 1. And we went through and said, hey, the momentum before the collision is equal to the momentum after. Let me be a little more specific now. I should say the translational momentum or the linear momentum before the collision is equal to the linear momentum after the collision. And we did this one, I think we did this one second. I think we did this one first, where they hooked together. But regardless of which order I did them in, we said that the momentum is conserved. And we asked this question, what would be the speed after the collision? And we had a little formula that looked something like this. We said take the momentum before and set it equal to after. And we said as long as you always include both objects that are interacting, momentum would be conserved. All right, I'm going to say the same thing. I'm going to say we have this principle called conservation of angular momentum. If we've got two rotating objects that interact, if you take the momentum before, it'll be equal to the momentum after. Now, of course, they're rotating, so I'm talking about a rotational or an angular momentum. And maybe a good example would be the similarity of this. Okay, so let's say, think about this translational one, and this will hopefully help me illustrate to you. If you're struggling with a problem, try to go back and think, how would I have done this if they were talking about a translational problem? So if I was having two objects, one moving and one stationary, and then they stick together, I would do conservation of momentum. So what if I had this problem instead? What if I had two objects? Here's a disk. Here's another disk. That disk is rotating. This disk is stationary. Doesn't that sound a lot like this problem? And now they're going to interact. And so what if I take the stationary one and drop it on top? What would be the speed of the two now that they've come together? And so let's give this a try, just like we would have done with the translation. I would have done this. I would have come over here and said, okay, how much angular momentum do I have to start with? And using this idea of angular momentum, I would say I had an inertia of the first one times the initial speed of the first one, then an inertia of the second one times an initial speed of the second one. That would then have to equal to the inertia of the first one and the final speed of the first one, plus the inertia of the second one times the final speed of the second one. And something like this applied to this problem, so this is more of a general answer, but for this one, again, just like I did for the stationary carts, I would say I've got initially one moving and one not. I think in that one I said number 2 was moving, so why don't I call this number 2? So number 2 is moving, number 1 is stationary. So if I did that, I guess I'd come over here and say, all right, number 2 is moving, but number 1 is stationary. So that first one would be a 0. And then I would say I2 omega initial for number 2. Now notice when I put them together, they rubbed on each other, and that's our conservation of angular momentum. This one right here, number 2 slows down. But number 1 speeds up. So this one loses angular momentum, this one gains it, the total doesn't change. But more than that, I would even say, because they stuck together, they're going the same speed. And there's no point in calling them angular speed 1 and angular speed 2. And again, just to remind you, I did exactly that back in chapter 8, where I said, okay, stationary number 1, moving number 2, they hit, and then I gave just one final speed. And then I said you could just think of this as one object now, and that's what we have. We can add them together. Now, when we did the translational one, I took another step and said the masses were the same. This isn't quite true, but I'll go ahead with that analogy and continue on. This disk is a little thinner than this disk. So this actually has a little more moment of inertia than this one. They have the same diameter. They're kind of made out of the same material, but this does have a little more mass. And if you remember the chart before the break, it was 1/2 mr squared, and so that has more mass than this one. But for simplicity, let's just say if they had the same inertia, then we could just call this an I. We don't need to say 1 or 2. There's only one initial speed, so there's no point in calling it 1 and 2. These two could add together, so I'd call it 2I times the final speed. Since I shows up on both sides, again, just like in chapter 8, we had mass, we could cancel it off, and we end up saying that the final speed is 1/2 the initial speed. And you might even remember me saying this. Doesn't that make sense? That if the momentum's got to be the same, you essentially have all the momentum here, and now you've doubled the mass. And so you have to cut the speed in half in order to have the same amount of momentum. And I'm saying the same thing. We've got to cut the speed in half because we've doubled the inertia in order to have the same amount of angular momentum. So again, same principle, conservation of angular momentum. A little harder to work with, but like I've said many times, I'm going to keep saying, hopefully you can see the analogy of what we did for translational motion, and hopefully it'll make the rotational motion work out. Although, something that's kind of fun to do with rotating objects, and I keep saying it, rotation's a little bit harder than translation because torque is more than force, moment of inertia is more than just regular inertia, which that means things like rotational kinetic energy and angular momentum are more than their linear counterparts. Because you could change the moment of inertia by changing where the weights are. We couldn't do that with translational stuff. Here, if this is moving and has a certain amount of mass, it doesn't matter whether the mass is in the front of the cart or the back of the cart, it still just has a total amount of mass. And so if the mass shifted around, there was nothing interesting to talk about. But for a rotating object, that can be very interesting. Let me move this out of the way. What if, and I'll put it in math form right here, what if I say I have a single spinning object? So I don't have even two interacting objects, just a single object. But the mass of that single object moves around. So if I were to write this as initial moment of inertia times initial speed, then equals to final over final speed. Notice then, the moment of inertia can change if you change the location of that mass. And this ice skater is a good example of that. She's got her arms out here spinning around. And so looking at her right now with her arms out, as opposed to what she's about to do, which is to pull her arms, and I think her leg too, yeah, and everything tightly in, that's going to change her moment of inertia. Now remember, moment of inertia has to do with how far out the mass is. So if you bring it in, it's going to go down. So this number goes down. So what does it say about this number? Yeah, it's got to go up. And by taking advantage of this principle of conservation of momentum, the ice skater then can change her speed by changing the moment of inertia. And you see this a lot in sports. A good example is ice skating. It's probably the best example, but gymnastics is another one. The diving competitions, if you watch the cliff diving or the platform diving in the Olympics, you know, that diver comes off and they tuck in everything real tight. And the purpose of that is to lower this number so this number would go bigger. So they don't have to push themselves while they're in the air to change their angular speed. Well, I'll illustrate it by pulling my arms in. I won't try to ice skate for you, but I will spin on this little stool, and to make it more exaggerated, I'll put some weights in my hand. And so if I start with the weights out here and give myself a little nudge, I'm going around, and I'd say I have a big moment of inertia. And if I pull them in, I go real fast and then slow. And then fast and then slow. And fast and slow. I could do this for a while. I like this. Okay, so there's our conservation of angular momentum. And like I said, you don't really have an analogy with that with translational because you can't change the moment of inertia. But you can then play with the moment of inertia, ice skater and this one. Here's another one too, if you like say motorsports, motorcycles, kind of a little different than the ice skater, like the same thing, but a motorcycle has other moving parts. So you might give some of your angular momentum to the other moving parts. Here's what I mean by that. What if I take, as an analogy, me, the rider on the motorcycle, and I go off this jump and I'm in the air and I've got the wheels spinning. I would say right now the two of us have a certain amount of angular momentum. Although in reality the wheel has it all and I don't have any. But if I apply the brakes, where does that angular momentum go? To me. And if I get tired of rotating, I can give it back to the wheel. If I give it a lot to the wheel, maybe I can even rotate the other way. See, because remember, it's positive and negative. And so by transferring the momentum, different objects, again, angular momentum, we could change the effect. So the motorcycle rider takes off, wheels are spinning, and you say, oh, apply the brakes in the air, that's not going to do any good. Well, it's going to change the angular momentum from the wheels to the motorcycle and the rider. And so as the motorcycle's in the air and you apply the brakes, now the motorcycle rider does this. And it's quite impressive feat to watch it go up, apply the brakes. Now the motorcycle does a flip, comes around, and then gives it just the appropriate amount of throttle to stop that rotation, and then continues on down and make the ramp. Or even more impressive to me is the one when the motorcycle goes up, whoom, they apply the brakes, whoo, they get about halfway over, then they give it full throttle. They give it so much throttle that the back wheel has so much angular momentum that the rider has to have negative to keep it a constant, and now the rider rotates back the other way. So it goes up, hits brakes, goes like this, oh, moves back and hits the landing. And so there's a lot of maneuverability, if you will, in the air using angular momentum, not the friction of the tires. I mean, just because you're in the air doesn't mean you can't control your mobility and how you move around here. In fact, you'll see it here if I just take this same wheel. Let me get it spinning. But I'll start this time with it in a horizontal direction, because when I turn it this way, I think you can see from above it looks like it's going clockwise. And if I turn it the other way, get rid of that rope, it looks counterclockwise. But when I get started here, I would say there's no rotation, no angular momentum. So if the wheel goes clockwise, I go counterclockwise. If the wheel goes clockwise, I go counterclockwise. The total angular momentum is conserved. And so we can transfer the angular momentum back and forth. And you've probably done this many times in your life, not even thinking about it. How do you ride a bike and turn, especially when you're riding a bike going fast? Well, don't you take the bike, and you got the wheel, and you're riding along. And if you want to turn to the right, don't you just lean the bike to the right? But see, from a top-down view, if you look down, turning that wheel to the right makes the wheel look like it's going in a counterclockwise. So you, the rider, go clockwise. so that the total angular momentum doesn't change. And again, you'll see that if I take myself as the rider here. So here's the wheel. I'm riding along, and I lean my bike. And I can control how much I turn as I lean the bike. And I take advantage of the angular momentum that's in the bike here. And so I've got this kind of this top-down view that had zero angular momentum because the wheels were going horizontal until I tilt the bike. And then I have to have this conservation of angular momentum. Well, believe it or not, better or worse, that is the end of the chapter here. And I think I'll go ahead and make some additional little videos to do some calculation. But since we are a little behind on the schedule, why don't I turn the page? What are we doing on time? Oh, good. We've got like 35 minutes, 40 minutes here. Let's go ahead and get started in the next chapter. We won't get too far into it, but we will set it up. I also want to say, as we close up this chapter, that this last section, 10.7, you can go ahead and skip on. Okay, it's just gonna be a little too much to do already in this chapter. So we're gonna do the first 6 sections, but we're not gonna focus on that last one. It's kind of a fun one, a little more advanced than I think is needed for this class here. And so that'll be a good next step. All right, Ron, why don't I have you hit stop for now, and we'll call this chapter a wrap.